Thank you everyone for joining today's webinar. So welcome everyone. I am Marwan Abbas, and I'm excited to be here to talk to you about a topic that's actually been asked from us a lot lately. So it's an interesting topic. So we're talking today about transitioning from FPGA to ASIC. And I know this topic can feel a bit overwhelming, but I promise by the end of this webinar, you'll have a clear understanding of the differences between FPGA and ASIC, why you might want to make the switch, and most importantly, how eFabless can help you make that switch and can help you bring your design to silicon. So let's start with a quick poll. So we're just curious how many of you are actually interested in doing the transition from FPGA to ASIC. So this is just gonna take a minute. It's a yes or no question, but we're very excited to show you how you can actually do that transition. So I'll just give you a couple of more seconds so that you can answer the question. And yeah, so thank you for that. And let's begin with the basics. So what exactly is an FPGA? So an FPGA stands for a field programmable gate array. These are configurable hardware platforms, meaning that an FPGA can be programmed and reprogrammed as many times as you want. Now, what makes up an FPGA? So an FPGA is made out of configurable logic blocks, or CLBs, and that's where the logic operations happen. And then we have the programmable interconnects, which are like dynamic wiring that connects different parts of your FPGA. And then we have the I/O blocks, which lets your FPGA communicate with the outside world. Now, beyond that, FPGAs also have additional features like embedded memories, DSP blocks for signal processing, clock management, and configuration circuitry. And because FPGAs are reprogrammable, they're perfect for rapid prototyping, iterative development, and real-time reconfiguration. So if you're in an early stage of the design and you need flexibility, it's a fantastic starting point. But what happens when you need something more optimized? That brings us to ASICs, or application-specific integrated circuits. So unlike FPGAs, ASICs are custom designed for a specific application. And once they're fabricated, their functionality is fixed. That means that you cannot reprogram them after manufacturing. But the trade-off here is that they're far more optimized. So let's break it down. The ASICs are made out of logic gates. These are the basic building blocks of digital circuits and interconnects, which are wires that connect between different parts of the chip. And then we have I/O interfaces, which are essential for communicating between the chip and external devices. And then we have the process design kit. This is not really a component, but it's an essential part of ASIC design. The PDK, or the process design kit, is a set of files that are provided by the semiconductor foundry that defines the design rules, transistor models, and standard cell libraries that are specific to that specific manufacturing process. So without a PDK, we wouldn't be able to ensure our design is actually manufacturable. In addition to the core components, ASICs often include additional features such as memory elements, analog circuits, and clock distribution networks that ensure that the ASIC operation is in sync. ASICs are ideal for high volume production, where performance, efficiency, and power optimization are critical. And that's why we see them in industries like automotive, AI accelerators, and network hardware. So let's compare FPGA to ASICs directly. So FPGAs are more flexible when it comes to reprogramming and reconfigurable hardware. And also FPGAs have limited analog support. It typically includes fixed functionalities for analog components such as PLLs or simple ADCs. While ASIC have fully customizable analog integration. So whichever application you'd like to do with an ASIC for an analog integration, you can do it. So you have maybe RF, you can do power management, you can do high performance sensor interfacing. Also, since FPGAs are built for general purpose applications, they really suffer from overhead in terms of performance. So ASICs are up to 5 times faster, 10 times lower in power consumption, and can be up to 40 times smaller. Also, FPGAs do have a faster time to market since they don't require fabrication and you can program and test them instantly, while ASICs have longer development cycle as they require validation, fabrication, and packaging before you can use them. ASICs also offer a strong IP protection, making reverse engineering very difficult. And while the upfront cost or the NRE is higher in ASIC, it's much cheaper when you are going to volume production versus FPGA. So in summary, FPGAs are great for prototyping, proof of concept, and development, while ASIC are ideal for final production, cost efficiency, and performance critical applications. So that's where eFabless comes in. With our ChipIgnite solution for rapid IC design and prototyping, you can really jumpstart your ASIC project with a fraction of the cost and effort traditionally required by ASIC. So we provide a proven open source SoC, which includes a RISC-V processor and essential peripherals, so you can really focus on your custom logic. Also, eFabless provides commercial and open source IPs, so you can plug and play instead of designing everything from scratch. And for just $9,750, you get real manufactured and packaged ASICs. And once you verify your prototype, you can scale it up to volume production through ChipIgnite as well. And here we're showing how ChipIgnite works. So we have a template chip called Caravelle, and there are other different template chips, but this is our pilot template chip. It has a RISC-V processor and a pad frame and an empty space inside. And that empty space is basically where you do your custom design. So you really do your custom design, you submit it to our platform, and then we do the integration automatically and send it to the fab or the fabrication facility. And then we send you back 100 chips plus the evaluation board that you can use to test your design. And of course, we have a pathway to low, medium, and high volume production. So next, let's talk about one important factor in choosing between FPGAs and ASIC, which is cost. So starting with FPGAs, they almost have no NRE cost, but the price per unit remains consistent relative to the volume production. Unlike ASIC, that start at a much higher cost due to NRE or non-recurring engineering expense, but their per unit cost decreases significantly as production volume increases. At low volume, FPGAs are definitely more affordable, the more affordable option because it avoids the upfront NRE cost. However, when you go to production, or volume or high volumes, the cost per unit increases for FPGA, which makes ASICs much cheaper at high volumes. And then comes Chip Ignite, that offers a more affordable entry point into custom silicon. It reduces the initial NRE cost, making it viable even at low volumes. And as the graph shows, Chip Ignite becomes cheaper than FPGAs earlier compared to traditional ASIC. So we're gonna take a quick minute to do the next poll. Should have it on your screen by now. Yep. Yeah. So please put in your answers. I'm gonna take a quick sip.
Yeah, Marwan, we have one question in Q&A about how many gates that you can get on full Chip Ignite and on Chip Ignite Mini, the size of an SRAM block, and so what would the trade-offs be between area for number of gates and SRAM?
Okay. Do you want to actually answer that, Tim?
No, because I don't know the number for the number of gates you can fit in a Chip Ignite off the top of my head.
I can give you. Sorry about that. Can give you a ballpark. 10 square millimeter Chip Ignite.
Okay. I'll have an echo, Andy.
Yeah. Oops. Trying again. Can you hear this time?
Yep.
In a 10 square millimeter Chip Ignite, it's on the order of 1 million gates. And the Chip Ignite Mini is about 1/4 of that, just under 1/4 of that. And then the SRAM size, David, do you have the commercial SRAM macro size off the top of your head?
I think it's around 300 microns square, maybe a little off. That's not quite, maybe a little bigger than that, but not by much bigger than that.
And number of bytes?
That's
That's a 4K, right?
4K.
Okay.
Yep.
Bytes.
Yep. Okay. Thank you for that, Tim. Okay, so I guess we can move on. So here I wanted to give you a real world example of just how efficient an ASIC can be compared to an FPGA. So let's say you want to create an audio player, and if you decide to build it using an FPGA, you likely need a bunch of external components. So maybe that's gonna use an ADC or an analog to digital converter to process audio signals, and a DAC or a digital to analog converter to output the sound, and possibly an external memory for buffering. So all of these peripherals are gonna sit outside the FPGA, increasing the power consumption, board size, and cost. So imagine you wanna do the same exact design, but in ASIC. Instead of needing an external ADC, DAC, and memory chip, you can integrate everything directly into your silicon. So you now have a single chip that does everything: processing, storage, conversion, all in a single chip. So that definitely consumes low power or lower power, smaller form factor, better performance, and a lower cost at scale. And now let's take a closer look at the design process difference between FPGAs and ASIC. While they start off similarly, ASIC does have more steps to it. So let's start with an FPGA design flow. So it starts with hardware description language. So you actually write a Verilog or VHDL code that describes your hardware, and then you do a pre-synthesis simulation that tests the functionality before synthesis to catch any early design errors. Then you do synthesis, which turns the HDL code to a gate level representation, mapping it to available FPGA resources. And then you do post-synthesis, timing analysis, and verification to ensure that you're meeting the timing constraints after synthesis. And then you do place and route. So the design is mapped to the FPGA's programmable fabric, then a post-implementation verification to ensure that you are meeting the timing requirements and the functionality. Then finally, you do the bit stream generation, which then you can take and upload to your FPGA. But in the ASIC design flow, it starts with the same step, which is writing the Verilog. The Verilog for ASIC is a little bit different than the Verilog for FPGA, and we're gonna cover that in a little bit. So after you write your HDL code, you do RTL verification to make sure that you have the logic is correct and you have a functional hardware description code. And then you do synthesis, which generates a gate level netlist that is optimized for ASIC implementation. And then you do design optimization, floor planning, place and route, and then you do gate level simulation that makes sure that you are still passing the functionality even after all of these steps, and that the optimization was done correctly. And then you generate the physical views that, and these physical views are actually the views that we send to the foundry in order to fabricate your design. And then you do a physical verification to make sure to ensure that the layout matches the design intended. And the final step is tape out, where the design is prepared and sent to the foundry for fabrication. But not to worry, eFabless provides open source tools used in ASIC development, including OpenLane that goes from RTL to the physical views, CocoaTB for verification, and pre-check and tape out that run actually automatically once you submit your design to our platform for final design validation before fabrication. And all of these tools are actually open source and free to use. So you don't need any license or anything to use those tools. And I just wanted to give you a quick glance of what it looks like to actually create an ASIC. It is really a couple of commands. So you can use OpenLane, which is an RTL to GDS compiler. GDS here is the physical view that we actually send to the foundry. So it is really that easy. You give it the RTL, you give it a configuration file, and run a couple of commands, and then you actually have a design that you can send to fabrication. So now we want to talk about some key things to consider when designing an ASIC and the common pitfalls coming from an FPGA background. So first up, IP integration. So unlike FPGAs, which comes with a lot of built-in configurable blocks, in an ASIC, you have to bring your IPs yourself. So the good news here is that eFabless actually provides a marketplace that has ready-to-use IPs, both commercial and open source IPs, to make that integration very easy for you. Next, let's talk about memory. So unlike FPGAs, where you have embedded memory blocks, in ASICs, they don't come built in. So you actually have to integrate your own RAM or memories inside your design. And also, of course, eFabless provides that for you on our marketplace, so it's easy for you. And now one key difference between FPGAs and ASIC is the I/O handling. So in FPGAs, tools can automatically infer connectivity when you use in-out signals, for example. But in ASIC, you have to explicitly define inputs, outputs, and enable signals correctly. And also clocking is another area where ASIC differs from FPGAs. The clocking infrastructure is already done for you in FPGA, but in ASIC, you have to design your own clock tree mesh to ensure proper synchronization. And also for resetting, you have to have a synchronous reset in ASIC to ensure that you're timing clean and you have a clean startup sequence, and that helps avoid unpredictability in your chip. And finally, verification. This is a big one because in ASICs, it's permanent, right? So verification is very crucial. And that includes simulation, formal verification, and in some cases, you can even do prototyping using FPGAs. So now let's look at an example for porting a design from FPGA to ASIC and how we can handle the different kinds of things that might come up. So in FPGA on the left side, we can see that we have an initial block that basically initializes the counter register to 0, which makes it like a default value. And then we have a reset that is actually asynchronous. So it's once you lower the reset, it's gonna do it immediately and won't wait on a clock edge. But actually that wouldn't work in ASIC, because actually in ASIC we do not have an initial block, and if you even put an initial block, the tools aren't gonna synthesize it. So you can in ASICs there is no default value for the registers, or actually the default values are unknown. So you really need to make sure that you have a reset sequence, and the reset sequence initializes the registers to a known value. And of course, as you can see here, the reset is synchronized with the clock, unlike an FPGA where it's not synchronized. So here, it actually waits until there's a positive edge for the clock in order to actually do the reset. And actually, a great way to leverage your FPGA skills is to use it to test your ASIC design before fabrication. So while this is actually not mandatory in ASIC, it's optional, but it might increase your confidence in your design and catch any issues early on. And the good news is that eFabless provides infrastructure to support FPGA-based validation to ensure your design is fully tested and functional before committing to silicon. So to make things easier for you when you're doing the transition from FPGA to ASIC, let's go over a checklist of things that you need to keep in mind while doing the transition. So we'll start with the design and planning and requirement planning. So the first thing is to actually know how much memory you need. So you need to check how much memory you need in your design in order to find the right IP for your memory, and see how many instances you need of that memory. And then the next step is to take care that and identify the digital and analog peripherals that you need in your design, because you need to explicitly integrate those IPs. Either you're gonna do it as a custom IP or an IP from the marketplace, but you need to know which kind of IPs that you need in your design. And moving to power and performance. So in FPGA, power consumption is already predefined for you, but in ASIC, you can customize it even further. So You can implement some techniques such as clock gating or power gating that would customize your power for your specific needs and your design's needs. So once your design requirements are clear and you have them done, you can start working on the RTL integration from FPGA to ASIC. Sorry. So we start by the clock and reset. So we have to ensure that all the clocks and resets are synchronous, and we have to handle anything that is asynchronous from FPGA, as we showed in the earlier example. And then if you do have clock domain crossing, or you do have several clocks in the same design, you really want to create some logic to synchronize these clocks. And then you'll see what kind of IPs that you already identified that you need to plug out of the FPGA design and replace with ASIC IPs. And then the last step would be to run your design through a synthesis tool, maybe such as OpenLane, that can help you find any issues, and it can actually run linting for you to make sure that you do not have any logic that does not work with ASIC design. And the last thing is to actually create an RTL wrapper that connects your design to the ASIC's top level. With the RTL modifications in place, verification is the next major step that you need to ensure you do before fabrication. So the design should be tested thoroughly using simulation and formal verification techniques to achieve high coverage. So unlike FPGAs, where issues can be fixed in real time, ASIC verification must catch all of the issues before fabrication. And that means that you have to run RTL and gate level simulation. And also, if you have analog macros, you want to run a SPICE simulation to make sure of the functionality and the performance that you're requiring are in the macros. And then if you are using both digital and analog and doing a mixed signal design, basically, you need to make sure that the integration between them is done correctly. And optionally, of course, if you want to do FPGA prototyping, that would definitely help you find any potential issues. Okay, so after verification, the physical design process begins, and that starts with generating your physical views from maybe using OpenLane from the RTL, or creating your own layout if you're doing an analog design. And then you do physical verification, which involves DRC, LVS, and DRC. And then finally, you submit it to our platform, and we run automated pre-check and tape-out flows, which basically does all of the physical verification and integration for you, and then send it to the fabrication facility. So that was all, and thank you so much for joining us today. So please join our Slack community, and if you have any questions, please ask us on shuttle@efabless.com. Thank you, everyone, and we hope to see you in our next webinar. See ya.